Now, for the rest of our day, we're going to skip section 4.6. We're going to talk about section 4.7, which has to do with counting. So, are you ready? I'll start. 1. Oh, we have a lot of work to do. Ready? 1, 2, 3. No, that's not the counting. I'm sorry. Yeah, we're not doing that type of counting. That would be easy. That would be nice. We just count it 1, 2, 3, 4, 5. What we're doing in this type of counting is counting the ways that something can happen. That's what this is called, counting. Counting the ways that some group of items can be structured, reordered, how many ways that things can occur. We're going to deal with words called permutations and combinations in a little while. The first thing we're going to talk about, though, is something called the fundamental counting rule. And it has to do with this. It says, let's say now that I have a coin and a die. We are going to count in this section how many ways procedures can happen. My procedure is I'm going to flip the coin, then roll the die. That's what's going to happen. And we're going to count up how many ways we can, how many combinations of outcomes we have in this case. So let's look at the coin. How many ways can you flip the coin? How many outcomes can you get when you flip the coin? You really can only flip the coin like one way, right? You go like that. But how many outcomes can you get when you flip the coin? 2 outcomes. Okay. How many outcomes can you get when you roll a die? 6. How many outcomes can you get together when you flip a coin and roll a die? Say that. Someone said I heard it. I thought I heard it.
Isn't that 12?
What, no? Okay. Let's do this a different way. There's how many outcomes for a coin?
2.
What are the outcomes? There's how many outcomes for the die?
6.
What are the outcomes? So if you get a head, could you get a 1, 2, 3, 4, 5, or 6? If you get a tail, could you still get a 1, 2, 3, 4, 5, or 6? So let me ask this question again. How many total outcomes do you get? You get head 1, head 2, head 3, head 4, head 5, head 6. How many is that? Tail 1, tail 2, tail 3. All together, you get your 12 outcomes. Do you see your 12 outcomes? How are you going to get from here to 12? Here's what the fundamental counting rule says. Fundamental counting rule says this. If you have one event that can occur m ways, and you have another event that can occur n ways, then together they can occur m times n ways. Here's why. For every outcome you have for the coin, you have this many outcomes for the die. Does that make sense? Every different outcome here, you still have 6 outcomes. If I had a coin with 3 sides somehow, I'd have 3 times 6, because every different change of this outcome means you still have 6 outcomes here. Are you with me on this fundamental counting rule? That's what the fundamental counting rule says. It says that if you have an event that can occur m ways, and another event that can occur n ways, Together, they can occur m times n ways. And the reason is, again, if you have m ways this can occur, for every way, your second event can still occur n ways. So we multiply every outcome here times every outcome here. That's why we get the m times n. Together they can occur m times n ways. What's kind of cool is this concept can be extended indefinitely, which is nice. Let me show you an example of that, and then we'll be done for today. Hey, have you ever forgotten your PIN number for your ATM? Have you? How many people know their PIN number for the ATM? What is it? Okay. Just kidding. Just kidding. I would never do that to you unless I really needed the money. This concept can be extended. Let's say that you forgot your PIN number. PIN number is usually how many digits for you guys? 4. Okay, good. So for a security code, security code, let's say that you need to make up, or you have forgotten your PIN number. You have no idea what it is. All you remember is that when you made it up, the first digit could not be 0, because typically you can't have a 0 on your first digit. It's like 1,000 could be the first one you can get. So with your security code, we know the first digit cannot be 0. What I want to know is how many PIN numbers do you have to check? Or how many PIN numbers are possible when you're creating this? So how many would you need to check if you completely forgot it? I mean, potentially check. Let's see. If the first digit can't be 0, how many options do you have for the first number? 9. It can't be 0. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So 10 is not a digit because it has more than one digit. So if you can't have 0 as your first digit, how many options do you have for the first one? 9. You have 9. You don't have 0, but you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Are you with me? You have 9. Now, how many choices do you have for the second digit?
10.
Can you pick the 0?
Yeah.
Sure you can. It is only for the first digit you can't. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how many, that's 10 digits. How many for the third one?
10.
There is, oh, that's close. There was no stipulation on that. Almost got nailed with the pen. Tragedy. How about for the last one? Scared me. This is a fundamental counting rule problem. Here's why. For every choice of your first digit, you have 10 choices for the second, 10 choices for the third, and 10 choices for the second, the fourth. Does that make sense to you? So every time you choose here, you have that many more choices. If I multiply those all together, that's how many total options I have for PIN numbers. How many is that? 9,000 total combinations. That means that if you, hey, let's extend this concept in our last minute here. If we have 9,000 total combinations, and you're trying to break into someone's ATM, I know what you guys do on the weekends. You don't fly me. Just kidding. If you're trying to break into someone's ATM and you get one shot at it, what's your probability you're going to get it right? 1 out of how many? 1 shot? Out of 9,000 will be the probability that you get it right on the first guess. Probability of guessing with 1 try. However, if you try again, that probability is doubled. Well, not doubled, I'm sorry. That probability goes up. Not necessarily doubled, I suppose. But if you try again, second try, that probability, if you try a different number, I mean, hopefully you don't try the same number several times. You'd be the worst thief ever. But if you tried like 100 times, you'd have, well, 1 out of 900, right? That's significantly better. Or if you tried 1,000 times, eventually you're going to get this, right? There's only 9,000 combinations, actually not that many. But your probability is still pretty low if you guess it once. But do you understand how the combination idea works and how the fundamental rule, counting rule, can be applied towards our probability? Some people feel okay on that so far. We're going to try a lot more examples next time, but we're going to end there today. So we're talking about the fundamental counting rule, and we're thinking that if we have a certain number of choices for each of these events, and now in our case for a security code, picking a digit is an event. So what we have here is an extension of the fundamental counting rule. It says you have an event of picking a digit, then you have this event of picking a digit, then another event of picking a digit, and so on and so forth, so you get 5 digits. Those are all separate events in this context. So what we're doing is figuring out how many ways can you pick the first digit? How many ways can you pick the second, and the third, and the fourth, and the fifth? Because for every choice you have here, you have a different number of choices for each one of these. For every choice you have here and here, you have a different number of choices. That becomes a fundamental counting rule problem. That means we're going to multiply each of those different choices to find out how many total security codes we have for a 5-digit number. Are you with me on this? Yes, no?
Yes.
Are you sure? Okay. So let's see how many choices we have for the first digit. If the first digit can't be 0 and it can't be 1, what that leaves you with are the digits 2, 3, 4, 5, 6, 7, 8, or 9. That's 8 choices there. Did you get 8 choices for the first one? So we've got 8 choices for the first digit. Here's what I'm talking about. For each of the 8 choices you have here, you could pick a number for this, couldn't you? So if you pick 1, I'm sorry, you can't pick 1. If you pick 2, let's say the number was 2. Let's say you pick the number 2. You could pick a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, or a 9 for that, couldn't you? That's this many, 8 times this many choices. For every choice you have here, you can pick those numbers. If I chose this to be a 5, I could still pick a 0, a 1, a 2, all the way through 9 for this one. If I pick that to be a 9, I can pick a 0 through 9 for that one. So for every choice you pick here, you have another set of choices here. How many do you have to pick from in that?
10.
Good, because I made no stipulations. I said you couldn't be 0 or 1, that means 8 choices. But here you certainly have 10 choices to choose from. How about for our third digit, how many? Yeah. Fourth digit? 5th digit? Why 9? Okay. If we multiply those things together, that's going to tell us how many possible security codes we have with a 5-digit number. How much is that?
72,000.
That's right. Fundamental counting rule says if you have a certain number of, an event that can occur a certain number of ways, for instance, we have 5 different events here, to find out the ways they can occur together, you multiply them. So we have 72,000 different codes. How many did we have with the 4-digit code? Yeah, and I only made one limitation. I said the first digit couldn't be 0. We had 9,000. So just by adding that extra little number, look how much many